Thank you for joining me. Today we are in research methods and we're starting our second last chapter on descriptive statistics. So we will go over some of the different activities involved with descriptive statistics, how it's analyzed, talk about the frequency distribution, ways that we present data, what is it? There are specific characteristics of a frequency distribution, the normal distribution, that are very helpful. So we're going to review measures of central tendency, variability, what exactly is included in a normal distribution, percentile rank, z-scores, Cohen's d, and correlations. So I will give you kind of step-by-step instructions on different calculations that you should be able to do. So when we talk about descriptive statistics, it's exactly what it sounds like. It's used to summarize essentially a data set, right? So that includes things like counting, anything that when we're talking about frequency, tallying, summarizing, that's all descriptive statistics. Correlations are also a very common analysis that we use for especially large data sets when we want to establish a systematic relationship between two variables. So when we say we're looking at a correlation, what we're looking at is how likely are these two variables going to move in a way that we can predict it, right? So we'll talk about correlations in a bit. Important also to keep in mind, again, our scales of measurement. Remember, we have 4 scales of measurement, and depending on the type of data you're collecting, that's going to determine what kind of statistic analysis you can do. So it's nominal scale. Remember that those are just categorical variables. We call that qualitative because it does not have a quantitative value. So examples of nominal scale variables would be gender identity, maybe ethnic group, hand dominance, right? Left-handed or right-handed or ambidextrous, eye color. These things are all different categories. They're not saying that one is better than the other. Ordinal scale variables are different categories, right? Just like nominal, but now we're talking about ranking. So there is some sort of magnitude, but we don't know the size of the magnitude, right? The levels are not equal. So for example, military ranking is one. Award placements, first place, second place, third place. We don't know the quantitative differences necessarily between them. Things like grade level, you might say, is ordinal. Interval scale variables are different like nominal, ranked like ordinal, but now it's called interval because the differences are actually specific and they're measurable, they're equal. So calendar days, IQ score, temperature, these are all interval scale variables. They do not have a true zero. So for example, 0 degrees Celsius does not mean that we have no temperature. When the zero is meaningful, remember we have ratio scale variables. So ratio scale variables are different like nominal, ordered like ordinal, they have equal intervals, but now you have a true zero. So anything you're counting or measuring with some like a ruler or a scale, that would be a ratio scale variable. So weight, height, response time, distance, those are all ratio scale variables. Any questions about this quick review? Okay, so when we are collecting data in our research question in many ways is going to determine the type of data we collect, the research question, and also, the different kinds of what our goal is. So ways that we can analyze data, we can compare group differences. Again, goes back to the research question. Are you interested in seeing, for example, if there's a difference between left-handed people and right-handed people in their driving ability, or how many accidents they have? You could be comparing group percentages. You could correlate individual scores. So if we are doing an experiment, for example, on the effect of caffeine on cognitive ability, you might be measuring it with some sort of cognitive test in which you are looking at the scores as how much is there a correlation between caffeine somebody drinks and how well they do in this cognitive assessment. You could also be comparing group means, right? So that's sort of average score for example, on people who drink caffeine versus people who do not. So those are the main ways that we really analyze research. And again, the method that you decide in terms of statistical analysis is going to depend on your scale of measurement and what kind of data you've been collecting. So when we compare group percentages, this is appropriate for nominal scale variables because all you can really do is look at frequency and that kind of idea. And it can still be really informative. So an example I like to talk about is there was a MetLife study on homework. So the participants were teachers, parents, and students, and it was a simple yes or no question, which is a nominal scale variable. The question was, do you believe homework is important? Yes or no? And then they looked at the frequency of yeses. So 83% of teachers, 81% of parents, and 77% of students said, yes, homework is important. Then there was a second question, follow up. Do you believe homework helps students learn? Yes or no? And this was really surprising because only 55% of teachers said yes, 59% of parents, and 29% of students agreed. So even though very simple questions, two simple questions, nominal scale variable, right? Categorical, yes or no, but it's actually quite revealing based on the percentages. So what do these results reveal? Well, majority of parents, students, and teachers do believe homework is important, and yet there's this contradictory belief that, not as many people say that homework helps student learn. So the follow-up I would have is then why do you think homework is important if you don't think it helps students learn? But very simple study, and it was only on comparing group percentages, but still quite revealing. So another analysis we would do, as I mentioned previously, is correlating individual scores. So you could do this if there aren't really distinct groups, right? You could see if two variables are relating. For another example, there was a study on sleep and academic achievement as measured by GPA. The research question was, is there a relationship between sleep and academic achievement? So here they're not breaking it down by gender identity or grade level. They just took, the scores, their GPAs, and wanted to see about maybe there was a question in the study about how much they sleep. So they correlated individual scores on hours slept and academic achievement and wanted to see, was there a systematic relationship between these variables? And it looks like they had 101 participants. So that's the number in parentheses that you see. The R is Pearson's R. And then the strength of the relationship was 0.20. So not a very strong relationship, right? We want to see something like 0.8 or higher. The p-value is what we call the significance level, and it's 0.048. So when you have a p-value of less than 0.05, it says that it is statistically significant. So although it's a weak correlation, it is statistically significant that there is a relationship between how much somebody sleeps and their average GPA. Any questions about this one? Hey, we can also compare group means. So in this situation, we are breaking down our participant group into different categories, right? So maybe we could say male identified, female identified, non-binary, or something like that. What we're looking at is we are comparing the mean score on a dependent variable for each group. So this is a really fun study in 2007, Wasik and Payne did an interesting investigation on whether people eat more based on environmental cues. So do people eat more when there is no environmental cue or reminder of how much they've already eaten? So what they did is they had people come into a restaurant and they didn't know, they were randomly assigned into two groups, right? So one group had the servers collect the chicken wings. So it's a chicken wing restaurant. They had servers collect chicken wings. In other words, it was a bus table. And other groups, they had an unbus table in which the bones and everything would just continue to pile up on the table. And they were interested to see, would this make an impact? And they divided it based on men or male identified and women or female identified. And it was quite interesting. So for an unbus table, in other words, the wings were piling up on the table. Men ate an average of 163.3 grams of chicken wings, and women ate an average of 207.3 grams of chicken wings. Okay, so that is if they saw the wing bones piling up. Now let's compare it to the group in which the wings were taken away, right? The bones were taken away, so they had no environmental cue, no reminder that how much they've eaten. Well, look at the difference. Men ate almost 100, actually over 100 grams more of chicken wings when they didn't see the bones on the table. Women still ate more, but the change was not as much. But this is an example of where you're comparing the group means. You're looking at a group mean of chicken wings eaten by men and chicken wings eaten by women, and you can see the difference. And so it was interesting because the impact of environmental cues clearly affected men more than it did women. But again, what I'm hoping to show is by these examples, you could see how different types of data and analysis can be very informative. And these are simply descriptive statistics. Another way we look at descriptive statistics is through distributions. So when we have distributions, what we're doing is we're basically graphing our data, right? Remember, the x-axis or the horizontal one is what we consider the independent variable, and then the y-axis is the dependent variable. And so the distribution is the way the scores would be scattered across, in this graph. It's a way of mapping information. So frequency distribution can be also translated into different graphs, visual ways that we're going to divide it. So let's take a look. So let's say you have a data set. If you were going to make a frequency table from the data set, I'm going to tell you the steps that are included. First thing you do is you're going to order the data from lowest value to highest value. Obviously, these are quantitative, right? So you're not going to do this for nominal scale variables. You're going to do this for ratio scale or interval scale variables. Then you assess the range, meaning what is the difference between the lowest score or value and the highest one? And then you make the table. Okay, so here's an example of a frequency table. When you order the data, what it does is it helps you see how often a certain value is appearing. So on the left is the score, and we have it from the highest score down to the lowest. What you should notice in a frequency table is every single value between the lowest score and the highest score is represented in the table, whether or not you have that actual value. So on the frequency, you can see there are several zero values. That's because we didn't have that score in our data set. But you still have to account for it in the frequency table. Any questions about this? Excuse me. All right, so how can we actually visually represent this frequency distribution? One way is through a pie chart. So usually we'd use a pie chart for a nominal scale variable. So an example here is how many kids are read to at home versus not read to. So you can do this as a percentage or by the raw value. Percentages are often more revealing. So here you have 80% of students were read to versus 20%. So a pie chart is a great way to visualize the data because right away you can see without knowing the numbers, wow, thank goodness a lot more kids are read to at home rather than not. And it's very easy to understand a pie chart. Another way that we would represent it is through a bar graph. Oh, here we go. So whereas the pie chart, right here, you just use literally it's a circle and it's called a pie chart because it marks off the different components. A bar graph is another way, and we've already kind of looked at that in terms of when we were doing interaction effects, right? But in interaction effects, that's a histogram, not a bar graph. So a bar graph is also used for nominal data. You'll notice in a bar graph, it's not touching, right? A distinct bar for each kind of information. So we'll see with a histogram that it's connected because we're talking about continuous data. Whereas for bar graphs, they're a nice way of representing how often does this nominal data value appear. So red 2, you can see that it's like, okay, so about 48 students or kids are red 2 compared to not red 2, which is a little over 10, like 11 students. Again, you can easily see that the vast majority of student or children are red 2 rather than not. Another way that we represent, sorry, wow, that didn't look good. Uh, information is through a frequency polygon. So it kind of looks like this. In here, this study was interesting. It's how many kids were saying they like their moms more than their dads. That's right. So the moms are with the orange line and the dads are with the blue line. And how many times did they say that they like them? So it's kind of an interesting study as well. So there's another way to represent it. Essentially, uh, frequency polygon, you're connecting the different dots of the frequency distribution. And then you have a histogram, which is essentially, it's connected, it's for continuous data for a quantitative variable. And I'll show you what that looks like. So with a histogram, this is where we talk about something called like the normal distribution. What are we paying attention to in a histogram? Well, we look at the peak. What are the high values in this distribution that we're looking at? We're looking at the tails. The tails are the ends of the distribution. Are they, most of the time in a distribution, we'll see that the tails are the extreme values, and there often are not very many values at those components. A unimodal distribution means there's only one peak, meaning there's only one high value in the table of values that you have. Bimodal means that there are two distinct peaks. And then symmetrical is how much do the left and right sides of this distribution look similar to each other. Okay, so let's take a look. So when you hear the term normal distribution, this is what we're talking about. So if you were to visualize a curve with these data points, you could imagine that it is only one peak, right? There's only one peak, and in that curve, it's fairly evenly distributed. So in other words, it's quite symmetrical. The other parts is you look at the tails, that there aren't very many values at each end of the tail. So those another component for a frequency distribution. These characteristics are really important because we will have normal distribution problems that we're going to be calculating later, and I'll talk about that. So here's an example of a bimodal distribution. So you'll notice there are two distinct values, which are really high, 0.4 and 0.8. They're not equally high, but they're still distinctly higher than the other values in this table. So that's what we mean by the bimodal. Also, remember we talked about symmetry. Well, if you have extreme scores, you are not going to have a symmetrical distribution. You'll have what we call a skewed distribution. If it's negatively skewed, which is the one on the left, it means there is an extreme score, a very low extreme score that is pulling the distribution be negatively skewed. On the other hand, if it is positively skewed, that means there's an extremely high score that is pulling the distribution that way. So that's what we mean when we say negatively skewed. It means that the tail is being pulled all the way to the negative side. If it is positively skewed, it means the tail is being pulled toward the positive side. And as you can notice, right, the tails are very low. It means that there aren't very many scores that are doing that. But you have one or a few extreme scores that are making the distribution skewed. Questions about distribution shape? Okay. So when we talk about measures of central tendency, what we're trying to do is have a single number that captures the essence of your distribution, right? How did participants score overall? And there are three measures of central tendency. You should be familiar from statistics, right? There is the mean, otherwise known as the average. So with the mean, what we do is we add up all the scores and then we divide it by the number of scores that we were looking at. You can only do this with interval or ratio scale variables. You cannot do this with nominal or ordinal variables. The median is the middle score. So if you were to order your values from lowest to highest, and then you take the medium score, that's the median. If you have an even number of values, you're going to take the average of the middle two. You can use the median for ordinal, interval, or ratio scale variables because what you're doing is you're ranking it, right? Basically, you're ranking it from lowest to highest. So it does not necessarily have to be, you don't have to have a true zero for that. So mean is only for interval ratio scale variables. Median, you can use it for ordinal, interval, or ratio scale variables. And then you have mode, which is just your most frequent score. So because you're just looking at frequency, you can use the mode for any type of variable at all. So that's really nice. So you can use it for nominal, ordinal, interval, or ratio. So if you were collecting only nominal scale variables in your proposal, then your analysis at most for central tendency would be mode. All you could say was what value appeared the most, frequency. If you are collecting ordinal scale data, then it would be either the median or mode. So it could be frequency or what is the middle score that you're collecting. And then if you're doing interval or ratio scale variables, in interval scale, you could do median or mean, and then ratio, you could do all three, right? Ratio scale variables, you could do the mode, you can do the median, and you could do the mean. So ratio scale variables among the different types actually gives you the most options in terms of statistical analysis. Any questions about these different modes of central tendency? Okay, so let's do a review of how you would calculate it. Remember, for mean, you just add up the scores and divide by the number of scores. For median, you would order the scores from lowest to highest, and then you would pick the middle score. If there's an even number of scores, you're going to take the average of the middle two scores. And then mode, it's simply, again, you would order it and then just find the most frequent score among all the scores. So for example, if I were to give you this data set of that frequency distribution, I might say find the mean, median, and mode for this data set. So for mean, you would add the data and then divide by how many. So the mean of this data set is 9.4. Hopefully this sounds familiar, right? In terms of median, what would you do? You again would order the data, and now you're going to look for the middle score or the middle two scores. So in this case, there were 15 values, right? 7.5. So the median is 11. So if you look at the scores, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? You have 15. So you divide by 2, and it's 7.5. So 1, 2, 3, 4, 5, 6, 7. 7.5 is like seventh and eighth value are 11. So the median is 11. So you'll see the mean was 9.4. The median is 11. And then the mode, you would look at the frequency table. What has the highest frequency? Well, looks like two of them, 12 and 13. So this is bimodal. So you can see that the measure of central tendency you decide to use could have different values, right? In a normal distribution, they will all be the same value. But if your distribution is not normal, so for example, it's bimodal here, you can see that the measure of central tendency you decide on will have different values. So it's really important you consider what is the most appropriate measure of central tendency for you to use. Let me give you an example. Housing prices. If you look at real estate values, they do not give you the mean. They give you the median. The reason is they know that there are very, very expensive properties. And if you were to take the mean, those extreme scores, extreme values would skew would skew housing prices to be even higher than what we know is the median housing price now. So if you have a data set that have extreme values, outliers, you don't want to use the mean because mean is very sensitive to those extreme values. You are more likely to use the median. It will give you a better sense of what the middle score is in that data set. And remember, if you are just using nominal data, the most you can do really is just frequency. How frequent are these scores appearing? Any questions about these measures of central tendency? Okay, so measure of central tendency gives us an idea, like it's one value that essentially summarizes how the different values are appearing in this data set. It's also important to know variability. So there are three ways that we look at variability. There is the range. So in variability, we try to figure out how different are the scores in this data set, right? What's the amount of spread that's going on? How far apart are the scores when we map them out? So range, you simply take the highest score and the lowest score, and that will give you a value, right? Remember, in the word deviation, it's how far from normal, how far from the middle is a score. So when we say standard deviation, what we're trying to do is finding the average difference between a value and the middle value, the mean. That's what we mean by standard deviation. So if you calculate standard deviation manually, what you're doing is you're going to take every single score in that distribution and subtract it from the mean, and then you square it and take the average of that. That's what standard deviation literally is. So it's the average deviation of scores from the mean. So let's take a look. Standard deviation is very important because it gives us an understanding of the population that we're looking at. Tells us how spread out the data is from the mean. So the further, the higher the standard deviation, the bigger the differences that are among our population or our sample. If you have a standard deviation of 0, that means that every single score is the same, right? Like there's no deviation from the mean at all. So the smaller the standard deviation, it means that we're going to expect that there aren't many differences among the scores. If you have a big standard deviation, then we're expecting a lot of differences among the scores. So again, if we think about this, this is a normal curve. What we see is the majority of our scores fall there in the middle, right? Within one standard deviation. We'll talk about this idea of the rules to help us do calculations. What's important to note is it's unimodal, right? There's only one peak. It's symmetrical. And we see that in the tails, there are very few scores with either really high values or really low values. All right, so if we have a small spread, this is what it would look like. The scores are very close to the mean. It means that if we were to have a test and we took scores, that means that very few people scored really low and very few people scored really high. So if we have a large spread, then you see it means that you have a greater variability among the scores, right? So the larger the spread, the more differences between the lowest score and the highest score. If you have a small spread, it means there isn't very much difference between the lowest score and the highest score, and that a lot of people scored on average. So these are important characteristics because you can do calculations. If you make the assumption that some data set is what we call normally distributed, then you can do some calculations. We call it the 68, 95, 99 rule. What does that mean? 68 means that 68% of the values in your data set are going to fall within one standard deviation of the mean. So that means you have the mean, the mu indicates a mean value for the population. And then you have within one in the pink one, right? The pink area, you're saying 68, or to be very specific, 68.27% of your data set are going to fall in that range. So if you had to make a guess, you would say, oh, okay, yeah, I think about, this, these scores, 68% of the group will fall within here. Now you want to be even more sure it's going to fall in? Well, if you say within 2 standard deviations of the mean, 95% of the scores are going to fall there, or 95.45% if you want to be very specific. And then within 3 standard deviations of the mean, 99% or 99.7% of the values will fall within that range. So this gives you a really good sense of trying to figure out how, if here's a really solid example. So this is true, this normal distribution happens in grades. It happens very often in nature, happens with weights. All of these things follow a normal distribution. If you remember in statistics, we say you have to have an N of at least 30 to see if something is normally distributed, right? So that's why if you're interested in differences among groups, the recommendation is that you have at least 30 participants per group. If you're interested, for example, it may be developmental stage, adolescents, adults, and children, early childhood, then you want to collect at minimum 30 for each group. And then if you want to even subdivide that even more, if you're looking at gender differences, then you're going to have to collect even more. So instead of 30 for young adults, and you're also interested in gender differences, maybe you'll collect 90, male identified, female identified, non-binary. So then you want 90 for each group. So the more you want to subdivide your sample, the larger the sample size you're going to need when you're doing a quantitative statistical analysis. So here's an example of like our IQ. The mean, we always know the average IQ is at 100. And let's say we want to say, if the IQ scores are normally distributed and there's a standard deviation of 15, what you do is you draw the distribution and you'd mark it off. So 0, right? That means that there's no deviation from the mean. The mean is 100, and that's right in the middle. Then we subtract 15, and that's 1 standard deviation below the mean, and that's 85. Subtract 2 standard deviations from the mean, and that's 70. Subtract 3 standard deviations from the mean, and that's 55. So that's, now 3 standard deviations below the mean of 100 is an IQ of 55. 2 standard deviations below the mean of 100 is 70, and then 1 standard deviation below the mean of 100 is 85. So now let's go the other way. Let's add 15. So each time what you're going to do is add the standard deviation and mark it off in the distribution. So 1 standard deviation above the mean is 115. 2 standard deviations above the mean is 130. 3 standard deviations above the mean is 145. So when you think about this, you could say, what scores do the middle 95% of participants fall? Well, middle 95%, based on that 68, 95, 99 rule, says that within 2 standard deviations of the mean, you'll have the middle 95% of scores. So let's look, 100 is in the middle. 2 standard deviations, the lowest score is 70. 2 standard deviations above the mean, the high score is 130. So you could say 95% of participants fall have an IQ of between 70 and 130. So you could do this with many different kinds of data sets. It's very important for all of you to remember this whole, 68, 95, 99 rule. Questions about this? Okay, nothing? Because we're going to have problems on this, right? So your homework problems are with the standard deviation, with a normal distribution. All right, so let's go on to percentile rank. Again, these are descriptive statistics. So with percentile rank, we're just looking at the percentage of scores that are lower than a score of interest that you have. So what you would do is you count the number of scores in the distribution below the score of interest, and then convert that into a percentage. And that's what we mean by percentile rank. So here's an example. Groot earned a score of 98% on his midterm exam. It was the second highest score. He was in a class with 45 students. So what was his percentile rank? So these are the parts of the problem that you need to know. You need to know how many students there are. So there are 45. He got the second highest score. So that means that 43 out of 45 students got a lower score than him. So let's look at the calculation. Out of 45, right, 43 scored lower than Groot. So let's calculate that. 43 divided by 45 equals 0.955. Then we multiply it by 100, and that's 95.5%. So in terms of percentile rank, Groot is in the 96th percentile of the exam scores. So in order to calculate percentile rank, you need to know how many scores there are, how many scores are lower than the score that you're interested in, and then you simply make that into a percentage. You would divide the number of scores that are lower by the number of total scores, multiply that by 100, and then you have percentile rank. So with percentile rank, the higher the percentile, if it has to do with, with grades, if you're then the better, right? Now, you have to think about the context of the problem. Being in the highest percentile is not always good, right? What if it's percentile of people with heart disease? You don't want to be in the 96th percentile of people who have heart disease, because that means you have a greater incidence of heart disease than 96% of the population. So always consider the context of the problem before you make an evaluation of whether or not the percentile is good. Any questions about percentile? Okay, so now another type of problem set with descriptive statistics has to do with z-scores. So the formula for z-score is z equals, right, in parentheses, you have to subtract the average from the mean that you're interested in and divide it by the standard deviation. So you have a score of interest and you have the average score. You find the difference between those two, and then you divide it by the standard deviation of that data set. Z-scores are important because what it does is it can equate two values from two completely different data sets and have two different unit amounts. Because when you are dividing by the standard deviation, you're taking the unit component away from it, right? So what the z-score does is it gives you an idea of how far above or below a mean the raw score is, right? It's expressed in standard deviations. It can help you identify outliers, and it helps you compare scores from different scales. What do I mean by it helps you identify outliers? Well, remember, an outlier is anything that's more than 3 standard deviations away from the mean. So if you have a z-score of 3.2, then you know that score is an outlier. And we'll do some sample problems afterwards. So these are, I'm just wanted to highlight different types of calculations that you should be recalling from your Math 63 or statistics class. Another important type of calculation is what we call Cohen's d, also known as effect size. So with the Cohen's d, what we're taking is we're taking the mean of your experimental group. Remember, so if you're comparing group differences, you subtract the mean of the experimental group from the mean of the control group, and again, you're dividing by the standard deviation. So with the effect size, what we're looking at is we're trying to calculate the strength of a statistical relationship, right? So oftentimes you'll see effect size calculated for what we call a meta-analysis. A meta-analysis is a type of research report that looks at a wide variety of different studies on the same topic to get a sense of how strong is this variable, how effective really is it. So if you want to say that the amount of sleep, if you want to see how big of an impact is amount of sleep on cognition, well, you could look at all the research that has been conducted over the last 20 years and then actually do track correlations that they find between, amount of sleep and cognitive ability, and then use the Cohen's d to determine how strong is that effect of sleep on cognitive ability. So if you find your Cohen's d is 0.8, then it's a really large effect size. You don't need a lot of participants to find this effect in a group. On the other hand, if you have a very weak or small effect of this variable, like 0.2 or lower, then that means you have to have a really large sample size to find this effect in a random sample. So a way that we might kind of compare effect size and Pearson's R, which is correlation, is an effect size of 0.8, you would be looking at a Pearson's R correlation of 0.5 or higher. A medium effect size, you're probably going to end up seeing a Pearson's correlation of 0.3, around 0.3. And a weak effect size, you're going to see Pearson's correlation of 0.1 or lower. So it depends on your topic of interest. You need to be looking at previous studies to kind of get a sense of how big of an effect is this independent variable on the dependent variable. And looking at a meta-analysis and effect size will give you a good sense of that. So if you are interested in something that, is determined to have a fairly small effect, then you need to have a really large sample size. If you are looking at something that has a large effect, historically has had a large effect, then you don't need as large a sample size for it. Questions about effect size? So in your proposal, right, based on the data that you're collecting, I do ask, what kind of analysis do you think you're going to be doing? And so this is why we have to do that recap of the scale of measurement, because it depends on what kind of data you're collecting, what kind of analysis you can do. So correlations, we've kind of discussed this before. It's pretty, straightforward. Positive correlations means that the two variables are moving in the same direction. As one increases, so does the other, or as one decreases, so does the other. That's a positive correlation. On the other hand, if the values are moving separately, then we call that a negative correlation, meaning as one goes up, the other value goes down. And then here are different types of scatter plot examples. So remember, a scatter plot is when you take your values and you are plotting it, right? And seeing where the values fall. You will never see a perfect positive correlation. But what you might see is when you plot all your values that, oh, look at that, like in the middle one, modest positive correlation, that generally speaking, the values are moving in a predictable fashion. That's the whole point to correlation. Are they systematically moving together in a predictable fashion? If, generally speaking, as one value goes up, the other value goes up as well, then we're talking about a positive correlation. What you don't want to see is no correlation, where it's like, oh, look at that no correlation graph. They're just all over the place. That knowing the value of one does not give you any sense at all on what the value of the other variable would be. But it's still a finding, right? So no correlation, probably shoe size and intelligence, right? That kind of idea. Perfect negative correlation, remember, it's moving in opposite directions. Again, you're more likely to see the modest negative correlation, where generally speaking, you're seeing the values go down that way. So you're not ever going to see perfect negative or perfect positive. You just want to get a sense of, is there a predictable way these variables are moving together? And that's what we're doing for correlations. Finally, here's some kind of benchmarks, right? So if we have a correlation or Pearson's R of below 0.16, we say that's a very low correlation, barely able to predict what the other value will be. 0.3 to 0.49, moderate to low. And what we really want to see are pretty strong correlations, 0.7, 0.89 values, 0.9 and 1.0 is very strong. So remember correlations, the value is from -1, that's a perfect negative correlation, to +1, that's a perfect positive correlation. These range of values is not indicating positive or negative, because what you're looking at is how far away is it from 0. 0 means no correlation at all, right? So if you have a value that is very far away from 0, whether it's positive or negative, then that makes it a stronger correlation. Something to keep in mind. Any questions about these different methods of descriptive statistics so far? Okay, let's take a look at some of the problems we would be solving. So again, I want to remind you about the idea of the normal distribution, 68, 95, 99 rule. Remember, within one standard deviation, you're going to have about 68% of your values. Within two standard deviations, approximately 95% of the values. And within three standard deviations, about 99, it's like 99.7% of your values. So here's an example of a problem I might give you in terms of normal distribution. The weights of stray dogs at a particular pound have a mean of 70 pounds with a standard deviation of 2.5 pounds. And then I will tell you, assuming the weights follow a normal distribution, here's one question. What weight is 2 standard deviations below the mean? So when you get a problem like this, what I recommend is you draw the little curve, put the 70 in the middle because that's the mean, and then just right off the bat calculate what the standard deviation values would be, right? So if you do, what is 2 standard deviations below the mean? You would multiply 2.5 by 2, right? And you subtract it from 70 because you're looking at below the mean. So 70 minus 5, 65 pounds, right? To make it easier, this is what I recommend you draw. Here's the curve. There's the 70 in the middle, which is the mean. And then just calculate what each value is for 1 standard deviation below, 2 standard deviations below, 3 standard deviations below, 1 standard deviation above, 2 above, and then 3 above. And this way, I could easily ask you questions and you can answer it, right? So if I were to say, for example, what percentage of these dogs have a weight of between 65 and 75 pounds? Well, if you look at this graph, you'll be like, oh, that's within 2 standard deviations. So about 95% of the dogs would have a weight between 65 and 75 pounds. So the idea of the normal distribution is really powerful, and you can answer a lot of questions with it. Any questions about how this one would work? Okay, so here's another way I could ask a question. Again, same scenario, weights of stray dogs, mean of 70. So here I have it drawn already for you, with a standard deviation of 2.5. The middle 68% of dogs weigh how much? So to answer this question, you need to remember middle 68 means within 1 standard deviation of the mean. So what are we going to focus on? We're going to focus on looking at what value is one standard deviation below and 1 standard deviation above. So middle 68 are within 1 standard deviation of the mean. So 68.5 is one standard deviation below, 72.5 is one standard deviation above, and then you come up with your conclusion between 68.5 and so the middle 68% of dogs weigh between 68.5 and 72.5 pounds. So another question I might ask is what percentage of dogs, so we're reversing it, have weights between 62.5 and 77.5? Well, then you look at your little drawing, and 62.5 is 3 standard deviations below the mean, and 77.5 is 3 standard deviations above the mean. And what we know from the 68, 95, 99 rule is that if we are talking about all the dogs within 3 standard deviations of the mean, we're saying 99%. So for the normal distribution problems, you have to have a really good understanding of that 68, 95, 99 rule and different configurations that you might have to apply it. Again, the easiest I recommend is you draw the little curve, mark where the mean is, calculate the standard deviations, 3 below, up to 3 below and 3 above, and then based on my question, answer it. Any questions about normal distribution problems? Okay. Z-score problems. So remember again, what we're doing with the Z-score is that we want to find out, relatively speaking, how values from even two different scales compare to each other. Okay. We are expressing it in terms of standard deviation. So here's an example. Bruce took an exam with 35 questions on it. His score was 20. The class mean of the midterm is 26.16 with a standard deviation of 4.52. Then the final exam has 100 questions. So you'll see these different scales, right? One exam had 35 questions, the next one has 100. On the final exam, Bruce's score was 65. The class mean of the final is 80 with a standard deviation of 14, which means that on the final exam, there was a lot of difference among the scores. So the question is, was Bruce's score on the final exam relative to his classmates better than his relative score on the midterm? The key here is relative to his classmates, because if we didn't have that, you could just take the percentages of how Bruce did and compare it, right? But what we want to know is, in comparison to how the rest of the class did, how did he do? So what you would do is you'd calculate the Z-score for both midterm and the final, right? So the Z-score for the midterm, right? The score that Bruce got would be the X minus the mean of class. So 20 minus 26.16, and then you divide it by the standard deviation. Well, Bruce's score was actually lower than the class average, so you have a value of negative 6.16. Divide that by the standard deviation of 4.52, and you have negative 0.136. So Bruce's score is 1.36 standard deviations lower than the class. So you have to remember how to interpret the values. Okay, in the final exam, you're going to have to interpret it for me. It's not going to be enough to just do the calculation. I want to know that you understand what it means. Now let's look at the final. So we take Bruce's score in the final, which is 65, subtract it from the mean, which is 80, and you divide it by the standard deviation of 14. So you have negative 1.07. So in the final exam, Bruce's score was 1.07 standard deviations lower than the class. So relative to the class, right, Bruce's performance on the final was better than on the midterm. Why? Because 1.7 standard deviations is closer to the class mean than 1.36 standard deviations. Any questions about the Z-score and what the interpretation is? Okay, so let's do another example. All right, so Diana took an exam with 40 questions on it. The class mean of the midterm was 30.5 with a standard deviation of 4. Her score was 33. Final exam had 100 questions. Diana's score is 88. The class mean for the final was 82 with a standard deviation of 12. So again, same kind of question. Was Diana's score on the final exam relative to her classmates better than her relative score on the midterm? So again, you would calculate the z-scores for each of the occurrences. Oops, sorry, that's kind of messed up. And then you compare the two. So what was the z-score for the midterm? Well, her score was 33 minus the class average divided by the standard deviation, and she got 0.625. So her score on the midterm was 0.625 standard deviations higher than the class average, sorry. Then you take the calculate for the final. 88 minus 82 divided by the standard deviation of 12, and it's 0.5. So now, you know she scored 0.625 standard deviations higher than the class in the midterm, and 0.5 standard deviations higher than the class for the final exam. Well, in this situation, she did better on the midterm than the final. Why? Because 0.625 higher than the average, 0.625 standard deviations higher is further away. It's a higher score on average than the 0.5 standard deviations. Again, think about the context, right? So remember, for Bruce, he wanted to have the standard deviation lower because he's below that class average. So you want to be as close to the class average as possible. But when you're talking about scores that are higher, you want to be as far away from the mean as possible because that means you got much higher score than the class. Any questions on these two? Okay, so that is my summary for the descriptive statistics and the types of examples that you have in your homework and the type of questions that you would have on the final exam. Again, I will do a review of all the different types of problems that you would have on the calculation component of the final exam. Any questions? We'll stop the